All right, so this question is from 2015, number 4, and it's a pretty straightforward question. I like this one because it's not too hard, not too easy. So we have two identical spheres, A and B, released at time t equals 0 from the same height as shown. Sphere A has no initial velocity at all. So sphere A just gets dropped from rest and it falls straight down, whereas sphere B is given an initial horizontal velocity. So sphere B is launched horizontally where we have an x velocity initial. However, Vy initial is 0. There's no vertical velocity for sphere B. It has no motion in the vertical direction at all when it's launched. Then it tells us that sphere B travels a horizontal distance d before it reaches the ground. The spheres reach the ground at the same time, even though sphere B has more distance to cover. So sphere A goes boom, straight. Sphere B does travel farther because it starts with a horizontal velocity. However, they both hit the ground at the same time. Okay, so first question, A. The dots below represent spheres A and B. Draw a free body diagram showing and labeling the forces exerted on each sphere at TF over 2, which means halfway down. The total time in the air was TF, so TF over 2 would be, somewhere like right in here. Not that that really matters because the answer we're going to put down, it would be the same if we would have done it here or if we would have done it here. Anywhere on that trajectory, these force diagrams would be the same. So sphere A is represented by that dot. The only force acting on sphere A, the only force is the force of gravity, which can be represented with mg. Well, let's call that mass of A times g. Now, sphere B, if it's identical, now notice they gave us these grid lines right here. The purpose of these grid lines is to make sure we're showing magnitude of the force. If these two spheres have the same mass because they're identical, the force of gravity should be identical. So if we draw this force as 1, 2, 3 grid marks, 1, 2, 3, then the force on sphere B, since it's equal mass, should also be the same. So we'll call that mass of B times G. And that is question A. Let's go on to B. All right, so B, on the axes below, sketch and label a graph of the horizontal. So we're focusing on the horizontal component of the velocity of sphere A and sphere B as a function of time. So again, our diagram was this. So sphere A was dropped. Sphere A just went straight down to the ground like that, whereas sphere B started with a horizontal velocity and traveled like that. So if we focus on horizontal velocity, ignoring vertical velocity, for this graph here, we're focusing on the x direction only, this way. Sphere A does not start with x or y. So we could write that down. For sphere A, there is no horizontal velocity initial, and there is no vertical velocity initial. As sphere A falls to the ground, at no point does it gain horizontal velocity. Sphere A has vertical velocity only for the whole journey to the ground. So therefore, horizontal velocity is 0. So let's diagram that. So right here, this represents 0. So the velocity of sphere A, and let's just say like right here, would be TF, because they defined that earlier. TF is the time spent in the air for both sphere A and B. Now, sphere B starts with a horizontal velocity. And assuming no air resistance, which we can assume here because it wasn't mentioned, we know that horizontal velocity remains constant. So the horizontal velocity that sphere B started with is going to remain the same through the whole journey. And of course, sphere B will be gaining vertical velocity, right? Because gravity is accelerating the sphere that way. So the vertical velocity is going to get bigger, but for this question, we're focusing on the horizontal velocity. So for sphere B, pick some value, it doesn't really matter. And we're going to say this represents sphere B. So there's sphere B, this is sphere A. The horizontal velocity remains constant. Okay, last question. In a clear paragraph length response, explain why the spheres reach the ground at the same time, even though they travel different distances, right? So sphere A travels a shorter distance, sphere B is traveling a farther distance. So why do they spend the same amount of time in the air? So right off the bat, the biggest thing you want to say here, you want to say that sphere A and B reach the ground at the same time. Reach ground at same time because time in the air is dependent on vertical or y variables only. And then you could even go on to say, and does not depend on x, well, we should say horizontal or x variables. That really is the most important thing right there. Time in the air depends upon vertical values and not horizontal values. So what other points do you want to make in your paragraph length response? So you want to specifically say, and I'm not going to write this out because it'll take forever, but the next thing I would write, I'm just going to say it and you could copy it. The next thing I would say is both spheres fall through the same vertical height and therefore have the same vertical displacement. So both spheres are starting here vertically and they end here vertically. They both have the same vertical displacement, which we're calling h. Next thing I would say, both spheres A and B begin with no vertical velocity. So neither of these spheres start with a vertical velocity. Sphere A has no velocity at all, x or y. Sphere B does start with a horizontal velocity, but not a vertical velocity. So this third point here, you're going to say both spheres start with no vertical or y velocity. And they both are accelerated vertically by gravity. The acceleration vertically for A and B is the acceleration of gravity. Okay? And then lastly, you could say, talk about sphere B. You could say sphere B does begin with a horizontal velocity, but as stated, this horizontal velocity does not affect time in the air because time in the air is only affected by vertical variables, by the vertical components.